Do a screen recording on what I talked about on and several things. The first thing will be on what are what's the end behavior for rational functions. And the end behavior sometimes is called long run behavior. In other words, what happens when we go very far to the left or to the right of the graph? What happens? Well, here, if it's y equals 1/2, it is a rational function because it's 1 is a polynomial function. It's just a simple constant. And the denominator is also a simple constant. And so the numerator and denominator are both rational. You usually would see some x's and some other things in there, but it's a rational function. And in the long run, this gets closer and closer to, get off of that, gets closer and closer to what value? Well, let's see. If this is 2, this would be 1. In fact, let me zoom in a little bit. You can see there's 1, and it's a half. It's a half all along this line. This is staying at a half, but you knew that already. Now, let's put an x in the denominator. Now, this curve avoids 0 because if x equaled 0, this would be division by 0, and you can't divide by 0, so this thing avoids at all costs the value 0. But if we're looking at long-run behavior, let's zoom out a little bit, it's getting closer and closer to 0, not a half this time. Here's 1, here's a half. This is getting closer and closer to x equals 0. The vertical asymptote, y equals 0. Here's y equal 0. And it's getting closer and closer and closer to that green line. It approaches that green line asymptotically. Now, if I made the denominator, let's put a factor in the numerator, like parenthesis x minus 1. Now, the degree of the numerator, if this was multiplied out, it'd be 1x. Degree is 1. The denominator is degree 1. And all of a sudden, it's back to being 1/2 as the horizontal asymptote. So if I write in here y equals 1/2, that's what the curve gets closer and closer to as we go towards the end, the negative end, or to the positive end of the graph. It approaches that. Okay, degree has a lot to do with this, so pay attention to the degree. Now I'm going to make the numerator have a little bit higher degree. I'm going to make it go to the second power. The degree of the numerator now is 2. The degree of the denominator is 1. If I take a degree 2 polynomial and divide it by a degree 1, I get a degree 1 polynomial. And a degree 1 is a line. Are you seeing a line? We still have the same vertical asymptote that x equals 0 is there. See, it's still there. This blue one is the vertical asymptote caused by the denominator being 0 at x equals 0. But we have a oblique or slant asymptote that has a slope of, well, look at the leading coefficient 1, leading coefficient 2, and it's of degree 1, so it's y equals 1/2 x. There's y equal 1/2 x, and if I were to move this down some, that's the slope of the line, that's the oblique asymptote. It looks like it's down about 1/2. Nope. How about down 1? That's pretty close. We're going to learn how to find that soon. But right now, I'm not going to worry about that. I just want you to see that the leading coefficients now are dictating the slope. Now, if I made this degree 2, they're now equal degrees again. And so if I were to divide them, I get a constant, and the constant would be 1/2 again. And see how I get that? Long-run behavior approaches the 1/2. Let's now change this 1 to A and this 2 to B, and I want you to kind of see, I'm going to change this 1 to an A and this 2 to a B, and just see, make a slider for these. See how this, when they're equal degrees, numerator and denominator, this is going to be ax squared plus some other stuff. This is going to be bx squared plus no other stuff. But the ratio of the leading coefficients is going to tell us the line y equals a over b is going to be what this long-run behavior is. If I change a, it still follows a over b. If I change b, it still follows the ratio of a over b. It goes off the screen, but it follows it no matter how far off the screen I go. Okay? So these leading coefficients are hugely important into understanding the long-run behavior. And if I make the degrees important also. Here they're equal degrees, and so it approaches y equals the ratio of the leading coefficients. If the degree of the numerator is 1 more, make that 3, we again get a line. And if I put an x here, the slope of the line is the ratio of the leading coefficients times x. It needs to be adjusted to be in the right place. It needs a y-intercept, but I'm not talking about that right now. I just want you to get the bigger picture here. If it was less, let's take the 3 and make it gone. Now the degree of the denominator is greater than the numerator. When that happens, the denominator is more powerful for very big but very far to the left for x numbers that are negative but large looking, or very big positive numbers. The denominator will be much bigger than the numerator, and this fraction will be, the denominator will overpower the numerator, so we'll get something like 1 over 1,000 or something like that, and it will go towards 0. So if I change this to 0, you will see that that's, even if I zoom in, that's what this curve gets closer and closer to. So to summarize, and there's some here that I haven't done yet. We'll start here. We'll call if the degree of numerator is less than the degree of the denominator then the graph will have a horizontal asymptote of y equal 0. The denominator has a higher degree than the numerator. The numerator is less than the denominator's degree, and so it's going to approach 0, as in this case. If they're equal degree, then they're going to be, so let's put this down, if degree of the numerator is equal to the degree of the denominator, then it's going to be y equals ratio of the leading coefficients. It's going to be, as I typed it in here, a divided by b. Ratio of the leading coefficients. Okay? So, now let's continue on here. What if the degree of the numerator is 1 more than the denominator? Well, then it approaches a sloping line that it'll have what we call a slant. Let's get the ifs here. If degree of the numerator is greater than the denominator by 1, is greater than the denominator. So if it's by 1, if I take the numerator, I take the denominator's degree and add 1, then they'll be equal. So the numerator is greater than the denominator by 1. Then I get a linear or line, oblique line, a slant asymptote, which has a slope of a over b, if we're thinking about a and b being the leading coefficients. Okay? And I showed that here. The leading coefficients are a and b, and so if I make y equals a divided by b and make it a line by putting making a first degree polynomial, and it has that slope. What happens if the degree of the denominator is more than 1? What if it was, come here. What if it was 2 more? The numerator is 2 more than the denominator. Okay, so let's make this 2 more. I'll decrease this by 1. So now it's 2 more. Now it's a little bit hard to see this. I'll try zooming in, but you kind of lose it a little bit. It makes a parabola. And so I'm going to put a square on this. And do you see the green parabola? If I were to slide that green parabola to the right, it would fit pretty close to that red line. Let's do that. Let's move it maybe 1 to the right by putting parenthesis x minus 1 to move it plus 1. Oop, what happened here? Oh, bad. I did it wrong on the x. Plus 1, close parenthesis. There we go. Oop, I moved it the wrong way. Minus, x minus 1. It's getting closer. Maybe it's 1.5. See how the red curve and the green curve now are kind of lining up. I'm just guessing on the number here. The main thing I want you to see is that the a over b is controlling the shape. Now, if I change the a, you see the red one gets wider and wider, and so does the green one. And if it goes to negative, it flips it over, but it's still kind of matching the shape of this original function. The a over b are controlling the shape of the parabola. If I make it 2 greater, or 3 greater, like 4, the shape becomes cubic. And you can see how the green is kind of matching up the shape of the red. There's still this problem that x can't be 0. So there's still this vertical asymptote in the red that you don't see in the green. But otherwise, the shapes kind of match. So it becomes, if the degree of the denominator is 2 more than the numerator is 2 more than the denominator. Denominator plus 2 is the numerator. So the numerator is 2 more than the denominator. Then you get a parabolic shape. Now, we're not going to deal much with that in this class, in this course. And if it was 3 more, it'd be cubic shape. If it's 4 more, it's quartic shape, and so on. We are going to focus our attention on just these first 3. Those are the ones that I want you to understand from this. Now, I've been doing this. Let's go back here. Let's go back to linear. And let's take this so it's only 1 more than the denominator, but I'm going to take the 4 out. And I'm going to do, let's say, x plus 3. The degree of the numerator now is the leading coefficient still a, and it's going to be x squared, so it's a square, and the denominator's single, so the degree of the numerator is 1 more than the denominator, so that's going to make it be a line. The slope will be a over b, leading coefficients, plus or minus something that we're going to figure out how to do later. But you can see it happening. Now let's talk about the other things. We still have a vertical asymptote at 0 because 0 would make the denominator 0. So that's still causing a problem. You also see that it goes through, has an x-intercept at plus 1. Just like we were doing in our last section, we deal with the numerator the same way. We get intercepts. It goes through plus 1, and it goes through straight through. So the multiplicity is 1. And at negative 3, it goes straight through. Now, I'm going to increase the denominator's degree by 1. So now it has it would have a horizontal asymptote at a over b. See it there? Leading coefficients again, same degree. But I'm going to increase the degree of the x plus 3 to squared. Now it's 1 more again, and so it's going to have a slope of a over b. But now with this being squared at negative 3, like we learned in the last section, this has to bounce at negative 3. Do you see the bounce off at negative 3? and it goes straight through at plus 1. If I squared the plus 1, it would have to bounce here. So let's put that in. Now it's bouncing at both of those. And the overall bigger shape is going to be a parabola. If I get far enough away, you can see that the shape, even though there's this asymptote in the middle, it's still a parabola. The other thing I want you to notice is that when the denominator is x squared, it approaches x equals 0, both sides going in the same direction. If it was cubed, but as it approaches from this side, it goes positive. The other side, it goes negative. So it goes in opposite directions. If it was 4, they both go in the same direction. If it was 5, this one's, the right's going up and the left is going down. They go in opposite directions. If it's 6, they go in the same direction. If it's 7, they go in opposite directions. So the multiplicity of the denominator is going to determine whether they both go in the same direction or opposite directions. Let's put a note over here. Oh, here. If the multiplicity of a factor in the denominator is demon. I better not do demon. In a TOR. And the denominator is even, then the curve approaches the vertical asymptote going in the same direction. In other words, both sides go up or both go down. And if the multiplicity of the factor of the denominator is odd, that's key here, either it's even or odd. If it's odd, they approach the vertical asymptote going in opposite directions. One side goes up and other goes DOW and down. There's how that works. I missed a parenthesis there. Put that parenthesis and a parenthesis. So that's the behavior as you approach an asymptote. Okay, so let's just check that. So I'm going to mess with the denominator here a little bit. I got a denominator x, that's 0 when x is 0, and right now it's going, let's turn this one off. It's as it gets close to 0, as we move in towards 0, this side's going up and the other side's going down. If it was x squared, they're both going up. If b was negative or positive, they'd be both going down, but they still are going in the same direction. Okay, what if I have, well, let's look at x squared and then have parenthesis, let's do x minus 2. So now I have a vertical asymptote at 0 because that's what makes the denominator 0. And they're going in the same direction because that factor's multiplicity is 2. And at plus 2, which makes this be 0, I have a vertical asymptote. So leaving those, there's one at 0, and there's one at x equal 2. You see how I got it there? And since it's a single, it should be in opposite directions. Well, I see one going up, so on this side there must be one going down. Oh, there it is. It was being hidden. Okay? Now, notice at plus 1, since that's degree 2, it's bouncing at plus 1. At minus 3, it's bouncing. Do you see it bouncing right there? At minus 3, it's 0, and it came down and bounced up and goes up off of it. If I only made this once, then it crosses at minus 3, still bouncing at 1. And now the degree of the numerator is 1, 2, 3, and the denominator is 3, so it's going to have a horizontal asymptote at a over b. When the degrees are equal, it will approach a over b, which right now is, you can't see very much. Let's move it off a little bit. So here it is, it's negative 0.4, and if I draw that line, you can see that this graph is getting closer and closer to that value, the ratio of the leading coefficients. A is 1.8, B is 4.3, and divided, they're this, A divided by B, and that's the ratio, that's where the horizontal asymptote is. Bouncing at negative 3, or crossing at negative 3, bouncing at positive 1, and has a horizontal asymptote, a vertical asymptote here, and a vertical asymptote at 0 because of this and the 2. Okay? If I make this, if I were to square this one, then instead of going in opposite directions, they'd have to go in the same direction. So let's see what happens if I square that. Instead of just moving this one, it moved all of these down, still crossing at minus 3, still bouncing at 1, and now it's going not to a over b because the degree of the denominator is bigger than the numerator. That's when it goes to 0. So the horizontal asymptotes become 0. Okay, that's a kind of a summary of what's going on here. Everything that happens in the numerator, let's do a summary. Everything that happens in the numerator talks about x-intercepts. Everything in the denominator is talking about vertical asymptotes. And the degree comparison between the numerator and denominator gives you an idea of what happens in the long run. What happens as x gets really large or really small. The multiplicity of factors in the denominator tell you the behavior of the graph near the asymptote. So we got behavior near the asymptote, the long run behavior, and the behavior at the intercepts. By the intercepts depends on the multiplicity of the factors. At the vertical asymptotes depends on the multiplicity of the factors. And on the long run, it depends on which degree is greater and by how much, or if they're equal, and often related to the leading coefficients, as we took notes over here. Okay, now I want to show you one other thing. I'm going to take this out. So now the degree of the numerator is 3, the degree of the denominator is 3, so it goes to a over b. You can see the long run behavior. The degrees are equal, and we have something that looks like this. We have a vertical asymptote at +2, and they're going in opposite directions because its multiplicity is 1. At 0, they're going in the same direction because the multiplicity is 2. And we have this. Goes through -3 straight through, goes through +1, actually bounces there. Now I'm going to change this to +3. So this says there should be an asymptote at -3, a vertical asymptote at -3, but at -3 there isn't one. And it says there should be a 0 at -3, but there isn't one. Now, you can see that these would cancel out. And so really I'm working with just what this is, except that in this whole thing, I can't use -3. Now let's just follow this curve by clicking on it and go to -3. -3 is right there. Look at the circle that my pointer is in. That's a hole in this graph. This graph looks exactly like if I didn't even have these two factors there. If I take that out and take that out, I've got the same looking graph. But if I put them back in, it looks the same. But this one has a hole, the other one doesn't. So if a factor in the numerator and denominator exactly match, then the curve will look like just like these, except that the curve will have a hole at whatever makes this 0. And to find the y value of the hole, let's see, at -3, the y value looks like it's down about -1.5. No, -3/4. If I go across over here, this is about -3/4. It looks like it should be about -3/4. See, that's almost -0.75, 3/4. And this is a little over. It's not quite exactly that. And I have not very nice numbers here, but to find that number, I can take the reduced form, get rid of that one, and then plug into this equation x = 3. Now I'm going to do that using a table for that equation, and if I put into this reduced form -3, it tells me that's what the y value is at the hole, right there. The hole is at -0.744. So you can find the hole's coordinates, the coordinate of the hole, even though you can't put -3. Let's go back here. Put these back in. Even though you can't plug in this one, if I here and say do a table on this, I can't put -3 into that equation. It's undefined there. So I can't put in -3 into this. But if I put it into the reduced form, So this equation, I can't put it in, but if I take this one and make a table and put in -3, I find the value, y value of the whole. The whole's at -3, this. So if there's so back here to notes. If a factor in the numerator equals a factor in the denominator in the denominator, there is, and I'm going to say likely, whole. There's likely a whole. And you can find the coordinates by reducing the function, cancel out the factors that match, reducing the function, and evaluating the reduced function, the almost similar function, just about the same, evaluating the reduced function at the whole x value. Now I'm saying likely because, let's go back to here. If I go back to this with the, let's get rid of this and this one, I'm going to get rid of that. I'm going to put back in the x plus 3 and the x plus 3. So this has a whole at -3. If this factor was squared, then one of them would cancel and the reduced function would still have a vertical asymptote at that place. And so there wouldn't be a whole because there'd still be a factor left. This would cancel one of them, but there would still be a vertical asymptote at -3. So that's why if there are more of these than there are in the numerator, then there won't be a whole, there'll be a vertical asymptote. In the other sense, if we have x plus 3 more often there, then that you can't use the -3, and so there'll still be a whole. If you reduce it by canceling that one with one of these, then you will have a value at it. It'll be it'll be a x-intercept in the reduced form, but there is a whole in the original one because it had that factor square and x plus 3. That one will have a whole. Okay? That's a lot. That's kind of what you need. Oh, and there's one more thing I need to talk about. If this was all multiplied out, it might look like, ax squared plus 4x minus 5. Nope. Minus 5. I'd have to factor this to find out where the x-intercepts are. Now this is saying there's one, I can't see them here. Doesn't look like there's an x-intercept. If I go down a little bit more, 6, I should have some x-intercepts. Let's make it 12. There should be some x-intercepts. I can't see them. I'm going to mute that one. It's going towards 0. If that factored, there would be some x-intercepts. Let's change this. Oh, now there's x-intercepts. I would have to actually factor this to find out what the exact value of these x-intercepts are. And if this was multiplied out, let's see, that would be x squared, x cubed plus 3x squared with a b in front of it. I would have to factor it. And so then to find out what if the degree of the numerator was more than the denominator, I'd have to use long division to figure out the oblique asymptote. So they talk about that in the book. You have to do some long division. I didn't get to that in class today, but you divide the polynomial in the denominator into the numerator, and you will find the equation of the oblique asymptote, ignoring the remainder, just the first part of the division. I'll talk about that more on Monday. Okay, I think you got enough to get started on your homework.